Hi everyone, welcome back to Math 256. This is Scott. Let's get started. What we're now going to do is section 1.4, where we are going to, for the first time, take on a category of differential equations that we can actually solve. So we had a small case of a type of differential equation we were able to solve, the easiest case, which was basically only a question of taking an antiderivative, because the differential equation that we had didn't even involve a y on the right hand side. But now we're going to tackle the category of what are called separable. Separable equations and applications. Alright, so here's the basic setup. The basic setup is if we are going to have dy dx equal to some expression that involves just x's and y's over here, we want this to be something that we can actually break into two factors, which will be just the x factor and the y factor. It's just a factor in x and a factor in y. And the reason why we want to be able to break it into some sort of factorization like this, where there's one piece that only involves an x and the other piece which only involves a y, is so that we can then do what is called separating the variables. So separating the variables. And the way that works is you just take the factor that involves the y and you collect it over with the dy part of the derivative. And you take the part that involves the factor with just an x and you put that with just the dx part of the differential equation. So essentially you rewrite the equation so that what we have is just something that involves a y times dy and something that involves the x times dx. So again, this only has a y and this only has an x. So we got something over here, something over here. Now this one is actually the same as just the classical factor in x. This one is going to be 1 over whatever the factor in the y was, but that's not important. We'll see how this all works. Then once we have this, we will integrate both sides. And while we're doing this, our strategy is going to be to collect the constants of integration and in particular we're going to put them on typically the x side. But just for now we'll say on one side. And then once we have got this, then our goal will be to solve for y if we can. Okay, let's now just see this in action. So as a first example, let's just take something of the form dy dx is equal to sine x over y. Okay, so what we have here is separated out already on this side into a part that involves only an x and a part that involves only a y. And the important thing about this is that the part that involves only the x and the part that involves only the y are connected by the tissue of multiplication or division, not by addition or subtraction. So what that means is we can multiply both sides of the equation by a y, we can multiply both sides of the equation by dx. We can essentially just do a cross-multiplying type operation here, and what we would have then is y dy is equal to sine x dx. Now this already probably strikes you as a bit fishy, and you're right, it is a bit fishy. This is not the way you're accustomed to seeing the little differentials, the dy's and dx's, behave. When you have seen an expression like dy dx before, you have typically just thought of it as being one unified thing, not a piece that could be separated. But in fact, actually, the dy and the dx that are part of this are very related to the dy and the dx in the integral notation, and part of the connection is this exact thing. We can take the ratio here of the differentials, and we can then rewrite that equation as basically saying that this differential quantity is equal to this differential quantity. But when we have these little tiny infinitesimal quantities like this on the left and on the right, it doesn't entirely make sense. It almost makes sense, but not quite. And so, in order to make it make total sense, what we just need to do is add an integration symbol to both sides, and then what that's going to give us is now a perfectly sensible arrangement. So what we see here is the integral of y with respect to y is equal to the integral of sine of x with respect to x. Now both of these can easily be integrated. So the integral of y is 1/2 y squared plus a constant, but I'm not going to write that yet, and you'll see why. And then over here, the antiderivative of sine is going to be negative cosine. And then now, at last, we'll write the constant of integration. So basically, there's a little ghostly constant of integration on this side, but it's not going to be our custom to even write that typically. We're typically going to just have the constants of integration already together on the right. And then you just want to solve this for the y. Now, a note as we go down the road here. Whenever we are just multiplying the constant of integration by a factor such as 2, that's going to produce another arbitrary constant. This c can be anything. When you multiply it by 2, then it can still be anything. It'll just be twice whatever it was before. So note. Multiplying an arbitrary constant by a factor, I should say by a constant factor, so it would be different if we were multiplying it by some factor that was a function that was not constant. But a constant factor produces another arbitrary arbitrary constant. So when I multiply the c here by the 2, in order to get rid of that 1/2 there, I'm just going to be producing another arbitrary constant. And for the purposes of disambiguation, I might just write them c2, c3, c4 until I got to the end of them. So here, returning to this, if I take the 1/2 y squared, which equals negative cosine x plus the totally arbitrary constant of integration c, then when I multiply both sides by 2, I'm going to have y squared is equal to negative 2 cosine x plus c2, and here if you want you can state that c2 equals 2 times c1, or you can leave that sorry, not c1, just c is what we were calling it. c2 equals just 2 times c, and if you want, you can just leave that out, or you can put that in if you want to be extra cautious. It doesn't matter. And then here, we can take the square root of both sides, and we get y is equal to the square root of negative 2 cosine cosine x plus c2. Or sometimes at the end, when you've gotten to the end of your chain of reasoning, even if you've been distinguishing the constants along the way, you frequently will not write this in a form like this, but you might just write it as a C again. A capital C in the context of these sorts of situations always stands for a totally arbitrary constant. So here you could write, or if we want to write it in a slightly ambiguous way, which is not really a problem, or y equals square root negative 2 cosine x plus c, and this is because, so as c is completely arbitrary. So on this, the notation is actually a little bit loose because arbitrary constants don't really need to be distinguished from each other. It's only if you are trying to be extra careful and make sure that you are making it clear to the reader that in the chain of reasoning here, the constant was different as we moved along, or you can omit that and just keep writing it as a single constant. Either way is totally okay. The notation on this is a little bit confusing, perhaps, but it is customary to take certain liberties when it comes to distinguishing these things. All right, another example here. So what we have in this case is going to be y squared dy dx is equal to y cubed minus 1 times secant squared x. So once again, our goal ultimately here is on the entire left, we want everything that has to do with y, and on the entire right, we want everything that has to do with x. So all the y's on the left, all the x's on the right. And that's why we call it separating the variables. And any equation where you can do that is called separable. So on the left, y squared over y cubed minus 1 dy. And on the right, we're going to multiply both sides by the dx, and we're going to have secant squared x dx. Now, once again, here what we have is a little bit of a strange looking expression with these differentials just floating around naked. It's not really quite defined yet. So what we do here is we again mask mask the nakedness of these differentials with an integral sign. So y squared, y cubed minus 1 dy, the integral of all that. And the integral of secant squared x dx. Now here we're going to have a little bit of an integration review. So this case is best approached, as you can see, by just a simple u substitution, because what you have on the top is a square, which is the derivative of what the bottom is, a y cubed minus a constant. If you take the derivative of that, you're going to have a square. Now there's going to be some factor in front, but we can live with that. So u substitution, if we make u equal to y cubed minus 1, then du is going to be 3y squared dy. And so if we look at the part that is actually floating around in our integral here, that's a y squared dy. So if I wanted to get that by itself, then I would have that y squared dy is equal to 1/3 du, which then means that the left-hand side here is going to just be the integral 1/3 du over just a u, which, so this is still just the left-hand side, which is just going to be then 1/3, and now this is the natural log of the absolute value of u, which, if we remember, and plus a constant, but we're going to collect all the constants on the right-hand side. So this is equal to the integral of secant squared x dx. So over here, moving down the line here, if we have the integral of the secant squared, this is actually a special function. We can actually recognize this particular case. So secant squared is famous. If you think back over the catalog of things that you know how to anti-differentiate, this secant squared is actually the derivative of tangent. So that's what we have here. Plus the constant. And then u was totally our fabrication. We invented u. So then what we're going to have to do is return it to the y's that it came from. So it's going to be 1/3 the natural log of the absolute value. It's important in this. Don't forget the absolute value. Y cubed minus 1 equal to tan x plus c. And so once again, we didn't even bother writing the constant of integration on the left. We collected them all together on the right, is what happened right there. And now we are going to have to solve this for y, and we're going to have to work our way from the outside in, taking each piece off. So first we get rid of a 1/3 by multiplying both sides by 3. So here goes with that. So that's going to give us the natural log of the absolute value of y cubed minus 1. And that's going to equal 3 times tan x plus. And again, if we want to be careful, we can change the letter, although commonly we would not even bother doing that. But for now, while we're still getting our feet wet with this, there's no harm in being careful. So C2 is equal to 3 times C1. Oh, not C1 again. We didn't call it C1, we just called it C. Okay, and then going down here, if I want to undo a natural log, I'm going to have to apply its inverse function, which is e. So e to both sides is what would cancel out that. So that gives us now the absolute value y cubed minus 1 is equal to e to the 3 tan x plus c2. So that's how you undo a natural log. You can just switch it to its inverse expression. Now, thinking about this, this is equal to e to the 3 tan x times e to the c2. This is a classic property of exponential functions that we can use. And then this we can call a third constant. So we can call this c3 e to the 3 tan x and so what that means is that here c3 is going to equal e to the c2. And because exponential functions would never produce a negative output, that means that c3 is going to be positive. Not a negative output, but not even actually 0, so it's going to be straight up positive. But now I can remove the absolute value by putting a plus minus on both sides. So it's going to be plus or minus c3 e to the 3 tan x. And now what that means is actually I can make this arbitrary constant equal to c4, which means, or which comes from us just saying c4 is equal to positive negative c3. Oops. C3. And what that then would indicate is that c4 is no longer positive, it might be negative, but what it isn't equal to is 0. So there's that. And then finally, we can start to get to the end of the line here. So we got y cubed minus 1 equals that. Add 1 to both sides and we get y cubed is equal to c4 e to the 3 tan x plus 1, which then gives us y is equal to the cubed root of c4 e to the 3 tan x plus 1. And then that, we would not typically write it in this form. We would use either a different letter like D or K or something like that, or an A perhaps, or we could just go back and call it a C again. Or D. Where D is an arbitrary non-zero constant. All right, now let's try one last example. This one is a little bit, an arbitrary non-zero constant. D is an arbitrary non-zero constant. Now let's try one more example of this. example C, where what we're going to have is dy dx is equal to 2 plus x minus 2y minus xy. Now, as written, this is not, it does not have the look of a separable differential equation because it is not written as factors. What we have are four different terms, and so there's nothing we can multiply both sides by in order to get all the x's and the y's each on their separate side. So here, what we're going to have to do is we're going to have to apply some sophisticated factoring techniques in order to rewrite this. In particular here, this is a case of doing what is called factoring by grouping. So factor by grouping. So what we have here is 2 plus x minus y times 2 plus x, which is going to, so this is still dy dx, dy dx. So this is now going to be 2 plus x times 1 on that first factor minus y for the second factor. So now what we have is finally in a legitimate separable form so that we can multiply both sides by something, divide both sides by something in order to end up with all the x's on one side, all the y's on the other. So now we can go ahead and do that. So here we go. So we're going to end up, when we multiply both sides by dx and divide both sides by 1 minus y, we're going to end up with 1 over 1 minus y dy is equal to 2 plus x dx. So those are the variables separated, but then we need to make it into an integral. So the integral of 1 over 1 minus y dy is equal to the integral of 2 plus x dx. Oops, and we'll wait for the plus c. So here, once again, we have got a good occasion for a u substitution. So the u substitution in this case would be 1 minus y, which means that du would be negative dy, which means that our integral here is equal to negative du over u As for the right-hand side, that's going to be a very easy one. 2 plus x dx. So here, what we've got is the negative natural log of the absolute value of u. Again, I'm not going to write the constant of integration even on the left. I'm going to put them all together on the right here. And here, we're integrating with respect to x, so that's going to be 2x. And then that's going to be x squared over 2. And then finally, this is the constant of integration that applies really for both the left and the right alike. So now what we've got here is negative natural log of the absolute value of 1 minus y. And over here we've got the 2x plus the x squared over 2 plus the c. Then we can multiply both sides by the negative 1, get the natural log, 1 minus y, negative 2x, minus x squared over 2 minus c. And there's no No point in even bothering with a change of notation for a constant that has just become negative. And then that means the absolute value, 1 minus y, is equal to e to the power of. And actually, when we have these big complicated expressions, it's also common to write it as exp. I'm not going to bother with that right now, but you might see it. And so let's make a note. Make a note of that. So note for complicated expressions, exp is used instead of just e to the whatever. But not always, just sometimes. It's a matter of personal taste. Okay, but over here we've got a very similar expression to what we had before, so it's going to be e to the negative 2x minus x squared over 2 times e to the negative c. And so now I'm going to just go ahead and rewrite that again as just c2 e to the negative 2x minus x squared over 2, where c2 is equal to e to the negative c. These are still the absolute value, 1 minus y, absolute value, 1 minus y. Okay, so then what that means is 1 minus y is equal to plus minus c2 e to the minus 2x minus x squared over 2. And so, once again, I might as well just call it a new constant. C3, C3 e to the minus 2x minus x squared over 2, where C3 is equal to plus minus C2. Alright, and in the home stretch here, we can just solve this. We could add y to both sides, subtract that from both sides, for example, and we get y equals 1 minus C3e minus 2x minus x squared over 2. And by the same token as before, this means that C2 is positive, and this means that C3 is just not equal to 0. Could be positive, could be negative, but according to this line of reasoning, we would not have gotten 0. Okay, so there's that. And now let's look at some specific applications of the kinds of things that create these separable equations. So separable equations frequently come into play, for example, in just a situation of natural exponential growth or decay. Natural growth and decay. So, for example, just population. Population. So if beta stands for birth, and then delta stands for death rate, then what we would get is dp dt is equal to just kp, as we already saw, but specifically k here would be equal to the difference between the births and the deaths. Now this would be, this is separable. And in particular, what we would get is that dp over p would equal k dt, and then the integration of both sides would give you, in this case, the natural log of p. In this case, it would give you just kt plus the constant. Then what we would get is just the absolute value of p is equal to e to the kt, e to the c. Same line of reasoning as it's always been. Well, I'll avoid taking too many unnecessary leaps here, but it is the same line of reasoning as what it has been in those two previous examples that were similar to this. So that's e to the kt, e to the c, and so that's the absolute value of p. So then p is equal to some constant, c2, e to the kt, where c2, which is equal to plus minus e to the c. So I put together, in this case, the two steps that I did separately before, but it's because it has gone down the exact same line as it has gone before. And so there's this, nc2 is not equal to 0. And then that gives us, all in all, the population as a function of time of just c e to the kt, where c is the initial population. This is exactly what it was, what we said it was, the time in section 1.1 when we also looked at this same sort of population model, and now we can see the reason for it. It's a separable differential equation, and so we were able to separate the variables and solve by this method. But by the same tokens, we have actually a whole family of very similar situations. So similar situations would involve, for example, interest. In particular, interest that is continuously compounded. And the way this is often written, dA dt is equal to RA, where A is the amount in the account, R is the annual interest rate. As a decimal. And then by the exact same chain of reasoning, because it's the exact same differential equation, we would get A is equal to, and here we could write it A naught E to the RT, where A naught is the principal, in other words, the initial amount. And then another similar case would be radioactive decay. Where dN dt is equal to negative k n. And this would lead to a similar path, which would give you n as a function of time would equal whatever the initial amount was, times e to the negative kt. And the line of reasoning here would be the exact same as what it was in the case of the population. All right. Now, there's a particular case of or a particular situation that needs to be considered in all of these cases, and that is the situation of singular solutions. So these are constant solutions outside the family derived by the above method. And these usually come from special values of y that make the derivative 0. So examples of these sorts of things would often involve having the specific value where y was equal to 0 in the case of something like the population model. So as an example, let's take the population. dp dt is equal to kp if p is constantly equal to 0, this is a singular solution. So remember, the 3-barred equals is a notation that means constantly equal to. Another example of something like this, it could be, for instance, let's take the case where in example A from above, which was I'm sorry. I misspoke. I do not mean example A from above. I mean, in fact, example B from above. So, from example B from above, then let's take a look at that one. So remember, the equation was y squared dy dx is equal to y cubed minus 1 times secant squared x. So if y here is constantly equal to 1, then dy dx will constantly equal 0, and we'll have a singular solution. So the usual family of solutions in this particular case had the form y. So the regular family of solutions had the form y equals 1 minus c3 e to the negative 2x minus x squared over 2. So this is the usual family of solutions, but here, this originally couldn't equal 0, but it turns out that if C3 does equal 0, then that actually is still a solution, but now it's a singular solution. However, now we can include this value as a singular solution. Okay. So there's that, and it's a little bit of a tricky thing, but you'll get the hang of it. The important thing is that as you are solving the differential equation through the method of separation of variables, you will often end up with some kind of stipulation on the acceptable values for your constant, and it may turn out that even the values that you wouldn't have gotten by the chain of reasoning that we produced, even the values that you wouldn't have gotten that way, might still be legitimate solutions, only they are outside the typical family, which makes them singular solutions. So there's that, and let's call it now a section. I'll see you next time. Bye.